Topic: Interference coordination for FD-MIMO cellular network with D2D communication underlying. Introduction to FD-MIMO and D2D communications. Full dimension multiple input, multiple output FD-MIMO enhances spectral efficiency through 3D beamforming. Device to device D2D communication allows direct links between nearby users bypassing the base station. Integrating FD MIMO with D2D introduces new interference management challenges in cellular networks. Motivation for interference coordination. Efficient interference management is crucial to maximize network capacity and user experience. D2D underlay introduces co-channel interface with traditional cellular users and D2D base. FD MIMO's 3D beamforming offers new opportunities for interfaces, separation and spatial reuse. Challenges in FD MIMO with D2D underlay. Managing interference among multiple spatial layers with densely deployed antennas. Ensuring quality of service QoS for both cellular and D2D users amidst complex interference. Designing scalable and adaptive interference coordination schemes for dynamic network conditions. System model overview. The network consists of FD MIMO base stations serving cellular users and D2D base sharing the same spectrum. FD MIMO employs 3D beamforming to direct signals spatially towards intended users. D2D links operate in underlay mode, reuse cellular spectrum, and introduce interference to both cellular and D2D users. Interference sources in the network. Intercell interference from neighboring base stations. Beamformed signals. Intracell interference caused by overlapping beams and D2D transmissions. Cross-mode interference between cellular users and D2D base sharing the same frequency resources. Interface coordination objectives. Maximize overall network throughput while maintaining acceptable QoS levels. Minimize interference impact on both cellular and D2D communications. Ensure fairness among users and adapt to varying network conditions and mobility. Power control strategies. Dynamic adjustment of transmit power for base stations and D2D devices to reduce interference. Employ algorithms such as interactive water filling and fractional power control. Then, balance between interference mitigation and maintaining sufficient signal quality. Beamforming and spatial multiplexing techniques utilize 3D beamforming to steer energy away from interfering users, exploits spatial degrees of freedom to enhance desired signal strength and reduce interference. Combine beamforming with user scheduling for improved interference management. Then, user scheduling and resource allocation. Allocate resources based on channel state information, CSI, and interference levels. Prioritize users with favorable channels and low interference potential. Implement adaptive schemes to dynamically assemble spectrum and spatial resources. Interference alignment approaches align interference signals in specific spatial or frequency domains to simplify cancellation, leverage FD-MIMO's spatial capabilities to facilitate interference alignment, enhance network capacity by allowing concurrent transmissions with controlled interface. D2D mode selection and clustering. Decide whether D2D pairs operate in underlay or overlay modes based on interference conditions. From clusters of D2D users to optimize spatial reuse and interface management. Use proximity and channel quality indicators to guide mode selection. Power control for D2D links. Adjust D2D transmit power to minimize interference with cellular users. Implement algorithms such as game theory based power control for distributed optimization. Ensure D2D communications meet QoS requirements while limiting interference. Coordinated multiplant COMP techniques employ joint transmission and reception among multiple base stations to manage interference. Use COMP to dynamically coordinate beamforming strategies across cell edges. Coordinated multi-point techniques employ joint transmission and reception among multiple base stations to manage interference. Use COMP to dynamically coordinate strategies across cell edges. Improve overall network performance and D2D coexistence through collaborative processing. Machine learning for interference management. Apply machine learning algorithms to predict interference patterns and optimize resource allocation. Utilize data-driven insights to adapt interference coordination schemes in real life. Enhance the scalability and responsiveness of interference mitigation strategies. Performance metrics and evaluation. Measure spectral efficiency, outage probability, and network throughput. Evaluate interference levels, fairness, and user satisfaction. Use simulation and field trials to validate interference coordination techniques. Future directions and research challenges. Develop intelligent self-organizing interference management frameworks. Address the complexity of ultra-dense networks with massive MIMO and D2D. Explore the integration of 5G and beyond technologies for seamless interference handling. Practical implementation considerations. Ensure compatibility with existing standards such as 3GPR, NR, and LTE. Consider hardware limitations and computational complexity of proposed schemes. Promote interoperability among devices and network infrastructure. Summary of key takeaways. Effective interference coordination is vital for the success of FD-MIMO with D2D underlay. Combining power control, beamforming, and scheduling can significantly mitigate interference. Advancements in AI and collaborative techniques promise further improvements in future networks. Conclusion and outlook. Integrating interface management strategies enhances network capacity and user experience. Continued research is essential to address emerging challenges in complex heterogeneous networks. Thus, Thank you.